Okay, I continue explaining chapter 2. We did yesterday 3 variable maps. Today we will continue with 4 variable k-maps. I want to list how do we count the minterms on a 4 variable k-map. We start with the 0, 1, 2, 3, 4, 5, 6, 7. And here is the 8. Be careful. Not here. It is here. 8, 9, 10, 11, 12, 13, 14, 15. So when counting them, you have to be careful about the location of the minterms available. And let me write them for you. This is the 0, 0, 0, 1, 1, 1, 1, 0. Same for here. You have 0, 0, 0, 1, 1, 1, and 1, 0. If you check the location that you have here, okay, it's going to be 1, 1, 0, 0. See? So this is minterm 12. Okay? So we start with the 1, 1, then the 0, 0. Okay? So this is going to be the location of minterm 12. So I repeat, how do we count them? We count them with the M0, starting with the M0. So this is 0, 1, 2, 3. The location of the 2 is here because I have 0, 0 and 1, 0. So this will be the minterm 2. How about the minterm 6? It is 0, 1, 1, 0. So this is minterm 6. We move to minterm 11. So this is going to be 1, 0 and 1, 1. And this is minterm 11. I have 16 locations in the 4 variable k-map, and I count them from 0 till M0 till M15. Okay? When you are working on minimizing using k-maps, you try to find the adjacent ones available. Okay? As I said earlier, they have to be 1, 2, 4, 8, or 16 in the case of a 4 variable k-map. Okay, so a single one, you have 4 variables. When you have a 4 variable, the answer is going to be one variable in the minterm. 3 variables, you have 2 ones, it will give you 3 variables. 4 ones, it will give you 2 variables. Take 8 adjacent ones, the answer will be only 1 variable. And if you have the 16 to be 1 or 0, it's either going to be constant 1 or constant 0, depending on if you have ones in the 4 variable k-map or zeros.
دكتور هذا السلايد ما فهمته.
Which one this?
Yes.
So here, if you are taking 4 adjacent ones together, the minterm that you are going to have will have in it 2 variables. So 4 adjacent ones will have 2 variables in it, let's say x1. But if you take 8 adjacent ones, it's going to have 1 variable, only x or only y or only z.
هلا 8 مثلا 4 ones فيهم يكونوا مثلا تحت بعض وفيهم
They
يكونوا
have to be
straight line.
adjacent. Okay, I'll give you the cases now. Pay attention. This is 4 adjacent ones. This is also 4 adjacent ones. It could be here on the corners, 4 adjacent ones. They could be also 8 adjacent ones. Or this 8. Maybe this 8. See how many cases do you have? All of these are cases of rectangles of 8 adjacent ones that you can take. It could be these 8. Remember that you can fold the k-map and the edges become adjacent. Or they could be these 8. Okay, so let me do this example for you. We have, let me draw it and we will create it together. Okay, so this is a 4 variable k-map, and I will draw. I want someone to help me to fill the locations, okay, of the minterms. So we start with
0.
wx and here the yz. So here is the 0, 0, 0, 1, 1, 1, 1, 0. We move here 0, 0, 0, 1, 1, 1, and 1, 0. So the locations, I will point to the locations with the laser pointer. 1 second. This is 0, 1, 2, 3, 4, 5, 6, 7. 8,
Yes.
9, 10, 11, 12, 13, 14, 15. So when filling these, okay, you need to be careful. I have 3, so 0, 1, 2, 3. So this is the location of the 3. So 0, 1, 2, 3. So here I have a 1. Okay. 4, 5. So 4, 5, 6, 7,
اللي مكتوب
8,
فوق هو Minterms.
9, 10, 11, 12, 13, 14, 15. See the locations of the ones. Did you all understand how did I fill the four variable came up from the Boolean
Doctor,
expression? Yes.
I have I have a question. If they give us the max terms, so we take the opposite,
Yes, you fill
or we
them with the
fill
zeros. Okay? You fill,
in the zeros, then we fill in the ones.
yes, you fill the zeros and you work on the zeros adjacent, not on the ones, if you are filling the max terms. Okay? So let me start now. I will repeat how I filled this. This is 0, 1, 2, 3. So this is the 3. This is the 4, 5. We don't have in the 6. So this is the 7. This is the 8, 9. So I have a 1 in the 9. 10, 11. So I don't have ones in them. And here I have the 13, 14, and 15. So these are the locations of the ones that I have. Okay, now I want to work on how do we cover the adjacent ones. I am going to start with, check this please. This is 2. This is a 2. Another 2. And here we have 2. So these are 4 adjacent, or they will give me now 4 minterms. I will start with the first minterm, okay? I will start with this one here, the one that I have here. So we start, I have, let me point to it. You have here, this is the minterm I am working on, okay? So notice please, W did not change and X did not change. So I have a W prime X. Y changed. It was a 0. No, it did not change. It is still 0. So I have a Y prime. Z changed from a 0 to a 1. So I don't have a Z. So my first term is going to be W prime X Y prime. So this is the first term that I have. Okay. I will move now to the this. Okay. Notice please. W was a 0. It remained a 0. So I have a W prime. X changed, it was a 0, it became a 1, so I don't have an X. I have a Y, I have a Z, so it is W prime Y Z. This is the second minterm. I will move to this
Doctor,
minterm now. One
where
second.
is the Z
I will, one
in the
second. I
first
will
one?
move to this minterm now. This is 1, 1, so W did not change, so I have a W. X did change, it was a 1, it became a 0. Okay, so I don't have an X. Y was a 0, and it is still a 0, so I have a Y. This is why I have a Y prime. Z was a 1 and remained a 1, so I have a Z. So this is W, Y prime, Z. Here it is. One last term, which is this. W remained W, X remained an X, and Y is 1 remained a 1, but Z changed. So it is W, X, Y. Okay? So find all the prime implicants. If you look at this figure, these are the K-maps. I want someone to tell me what are the minterms that I have ones in them. Can anyone tell me, please? The minterms?
0,
0,
2,
2, 3,
3,
5,
5, 5, and 7.
7, 8,
Okay, بترجع 8,
9,
9, 10,
10,
11,
11, 13,
and 15.
and 15. Did you see how we count them? So you should be very quick in filling the ones and in reading the K-map, okay? I want you to notice, please, how do we take prime implicants? I mean by prime implicants, adjacent ones. So this is a prime implicant. Do you see it? This is another prime implicant. I have these 4. I can take the 4 corners. I can take these 4. I can take these 4. See? I have many. What I will do now, I am trying to explain what is an essential prime implicant. I mean by essential, it is the only way I could cover. This is called essential prime implicant. I will start with the essential. So this is the first. I have no other way of covering these four. And I have these four. Okay, these are called prime, essential prime implicants. How about I look at these two now? How about I look at these two? I have two ways to cover them. I can either take these four or I take these four. Since these two have two ways to be covered, they are not called essential prime implicants. Okay? So only the two essential prime implicants is this square and this. Okay? How about these two? I could cover them only either with these four or with these four. How about this one, please? I have two ways to cover. I can either
We
cover with these four or I can cover these two with these two. This is why we do not call them essential prime implicants. So I have two essential and the rest are not essential. Okay? We move to what do we call a don't care. Don't care, sometimes a function table or a map does not give me an output for two reasons. Maybe I do not have the specific output for the case, okay? Maybe it is not applicable. I'll give you an example that we did earlier, which is called BCD, binary coded decimal. There were only codes from 0 to 9. But the codes that were from 10 till 15 never occurred in the table. How come? Because we do not actually have 10 to 15 in the BCD. BCD stops at number 9. These are called don't cares, and we don't write a 0 or a 1, we write an X. X refer to the entry of don't care. We don't actually have a value for. How is a don't care represented in a K-map? When representing don't cares, you have to represent them in sigma D 1, 4, 6. What does this mean? These are the locations of the don't care in the K map. Sigma M means these are the location of the ones in the K map. Okay, these are the locations of the X in the K map. Okay, if you look at it, let me solve it for you. We will fill them together. So I have this four variable K map. How did I decide for variable? I have A, B, C, D. So here comes the A, B, and here comes the C, D. And I fill the 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay? When filling in the values, I will always have to list in my mind the location. It is 0, 1, 2, 3. So that's my 3. 4, 5, 6, 7. And where is the 8? At the very bottom. So here comes the 8, 9, 10, 11, 12, 13, 14, 15. Did you see how I filled it? So this is how you fill the sum of minterms in the K-map. I am also given the sigma D, which are the don't cares. Do I fill it on the same K-map or on a different one? No, on the same K-map. I will start now with the don't care. I have a 0, 1, so that's my don't care. It's a 1. Okay, 2, 3, 4, 5, 6. So these are the locations of my don't cares. I will repeat them so you understand them better. 0, 1, so this is the 1, 2, 3, 4, 5, 6, 7. So 1, 4, and 6 are don't cares. How do don't cares help me in my answer? When I'm creating a solution for my sum of minterms, if the x help me, I replace it with a 1. If it does not help me to find a solution, I ignore. Okay, so let's start now, please, with how do I want to cover my minterms or my ones. Be careful. I have here, please, a 1. Okay, I have here a 1, okay? What are the ways for me to cover this 1? I can take this 1 with this 1, agree?
With the X
The best way
or with the
is
one
to take it
on
with
the
the
bottom?
X. So I take these two with these two. It will give me 4 adjacent ones. So let me draw it for you. And this is 2 and these 2. Did you see it? So this X, which is I don't care, helped me in my solution. So I replace it with a 1. Okay. Now I want to think about this one, please. This one here. How do I cover this one? I can take these two with these two. This is a solution. But I can also take these two. These 4. Do you see? Did I need the X in this case? No. And all my ones are covered. So no need for me to use the X that I have in location 4 and in location 6. So I disregard them. Okay. So this X was required. So I replace it with a 1. However, this X was not helpful to me. So I kept it as an X. What are they doing here? They are not solving for the f, they are solving for f prime. Okay, so I will do the f for you and then we will do the f prime. Okay, guys, I will start with the f that we are having. We start here. Okay, we start here with these 4, please. What are they? I have an A, I have a B, okay, and the rest of CD are changing. So this is A, B, okay. And now I have the locations of these two with these two, okay. So how do I solve it? A is changing, it was an A, it became a 1, so I don't have an A. B was a 0, it remained a 0, so I have a B, but it is a B prime, right? C was a 0, it is a 1, so it changed, so I don't have a C, and I have a D. It is going to be BD. So this is the B prime D, sorry. So this is the answer. Okay. Now, what are they doing here? The question says here, use f prime and complement it to get the result. What they are doing here, they are looking where do you have your zeros. So you actually fill the rest of your values. Notice what I will do. Do you see, please? How do I fill the rest with the zeros? Who can help me now? Cover my zeros. Yes, please. When covering the zeros, you look at the x also. Okay, so if you have an x and it can help you in your solution, you actually try to take it. Okay, so I'll give this here. Notice, please, this x helped me in my solution. Okay, so it is going to be a prime b. You see, this is the first term. It is a prime b. This is a prime b. Now I have 4 corners that I can take. So 1, 2, 3, and a 4. And this is going to be A changed, B did not, so it is B prime. C changed, D did not, and it is B prime, D. So the 4 corners that I have are B prime, D prime. Okay? Can someone tell me, please, what happened from here to here?
Distribution.
This is De Morgan's law, if you remember, okay? And we did De Morgan's law for the f prime. It is b plus d into a plus b prime, okay? So this is how you could use the don't cares to help you in your solution. I will move now to new type of gates, which is the buffer. The buffer is a gate, which is only a buffer that stores your value. If you have an x, the buffer will give you an output of an x. If it is 1, it will give you a 1. If it is a 0, it will give you a 0. Okay? In terms of Boolean function, a buffer is the same as a connection, as if you have a line. Why would we use a buffer? Only to store. Okay, a buffer is like an electronic amplifier. It improves the voltage. So if it is below 1, it will amplify it to 1. That's the only purpose of a buffer. I will start now with an AND gate. So very quickly, let me write for you the truth table of an AND gate. So this is X, Y. I have 2 zeros, 2 ones, 0, 1, 0, 1. And the AND gate is going to be 0, 0, 0, 1. You agree? This is the AND gate. Okay, what about the NAND gate? It is an AND with an inverter. This is why we put a bubble here. It is an AND with an inverter. Okay, invert the AND. It's going to give you 1, 1, 1, 0. You got the idea? So how do you get an output from an AND gate? It is going to be X dot Y dot Z all bar. Okay? So X dot Z dot Y dot Z bar. So this is my XYZ, and the output that I am getting here is X dot Y dot Z all bar. Clear? So this is called a NAND gate. We also say not AND. The AND function with a not applied to it. So you have an and you put a not on it, it will be called an AND. Okay? The small circle that you are viewing, or the bubble, it represents the invert function. If you look at the Morgan's law, okay, you could also represent an AND gate with an inverted input. So you look at the OR, okay, check this please. You have X dot Y dot Z. What is the gate here, please? What is this gate? It is an AND gate. Put a bar on it. What is this gate? NAND gate. Okay.
NAND.
So doing the Morgan's law, it's going to be X bar plus Y bar plus Z bar. Do you agree? Okay, so what is the gate now that I have? It is an OR. And every input to the OR gate is inverted. This is why they put a bubble here. Okay, let me show you. This is why they put a bubble here, because X bar, Y bar, Z bar with an OR gate, it is equivalent to a NAND gate. So you could either symbolize or draw it as an AND gate with an invert. Okay, so let me draw it here again for you. So it is an AND gate with a bubble, and you have the 3 inputs. This is a way of drawing. Or you could draw it with an OR, but your input are bubbled. You got the idea? So you have here 3 bubbled input. See the difference? So this is an AND gate, and this is also an AND gate. The first NAND gate is represented with an and the second is represented with an OR. You got the difference? Okay, we continue. The NAND gate is a natural implementation for the CMOS technology. In terms of chip area, and all the CMOS chips, they use NAND gates in them. The universal gate of it, it's a gate that can implement any Boolean function. We have to know that the NAND gate is a universal gate. It does not have a symbol. This is the symbol of the AND. This is the symbol of the OR. Okay, you could also write it with a dot. So that's the OR, and that's the AND. Okay, so the OR is a plus for AND. We do not have a symbol operation for the NAND. Okay, it is X dot Y bar. This is how we write it. This is the NAND gate. It does not have an operation symbol for it. Okay, when you are doing X dot Y dot Z, you could use one NAND gate for it, one AND, sorry, gate for it. But if you are doing X dot Y dot Z كلها bar, and you are doing an AND gate, you cannot use one NAND gate for it, so it is not associative. Okay, we have difficulty dealing with non-associative mathematics. NAND is a non-associative operation. Okay. I will do now the NOR gate. The NOR gate, it is also a universal gate. How do we represent it? We represent it with an OR gate with a bubble. Okay, let me draw for you I'll create the truth table. This is x, y. So you have 0, 0, 1, 1, 0, 1, 0, 1. What is the OR? It's a 0, 1, 1, 1. So this is the OR. If you want to create the NOR in a truth table, it is the complement of OR. So it is 1, 0, 0, 0. You got the idea of a NOR? NOR could be represented as an OR with a bubble, or it could also could be represented, let me show you. It is X or Y with a bar. Do you agree? This is the NOR. Use De Morgan's law. What could you write about that? It is X bar dot Y bar. You agree? So this is an OR gate, and this is also an OR gate. The first OR gate is represented with an OR and a bubble. The second NOR gate is represented with an AND but inverted input. So see, this is an AND with inverted input. So this is also an OR gate, and I will draw the other one, which is an OR with a bubble. Okay, and you have two inputs. So this is an OR, and this is also an OR. The first is represented with an AND gate, the second is represented with an OR gate. You got the difference between the two? Okay, so anytime you have a logic diagram and I ask you to map it to an OR gate, you should know how to convert every OR to an OR and every AND gate to an OR. Okay, so this is going to be explained better, and you will have questions about it in chapter 3. Okay, so the NOR gate is also a universal gate, and we do not have a symbol for the OR. I repeat, it is X plus Y bar. So I don't have actually a symbol for the NOR. Okay, NOR is also not associative. Okay, we move now to XOR. How do you write the symbol of XOR? It is X XOR Y. So it has a symbol, the XOR. Okay. What about the XNOR? It is X XOR Y with a bar. So this is the XNOR. Okay. So what is XOR? You will have two different output to give you a 1. Sorry, 0, 1 will give you a 1. 1, 0 will give you a 1. 0, 0, they are the same. They don't give you a 1, they give you a 0. So let me show you the truth table of it. So 0, 0, notice please they are the same, it will give you a 0. And if you have different input, so 0, 1, it will give me a 1. So what do you call this table? It is the X XOR Y, and they must be mutually exclusive. When I say mutually exclusive, I mean by that they must be different. 0, 0 are not different, it will give me a 0. 1, 1 are the same, it will give me a 0. How about the XNOR? XNOR is the complement of XOR. They must be equal to give you a 1. You got the idea? Notice please here 0, 1, 1, 0 is the output. Here it's the complement. It is 1, 0, 0, 1. We call this mutually exclusive. We call this equivalence. Okay, they must be equivalent, so I get a 1. Here they must be different, so I got a 1. You got the idea between the two? So XNOR is referred to as equivalence, whereas XOR is referred to, or XOR is referred to mutually exclusive. How do we draw how do we draw XOR? Notice please, it is an OR gate, exactly the same, but it has a double line here. So this is XOR gate. It looks like an OR, but we add a line before it, it will be called a XOR. How would you draw an XNOR? You put a bubble on it. Okay? So you have a rule saying that if you are doing X XOR Y, you notice X and Y must be different. So X Y bar or X bar Y. Whereas when you are doing X XNOR Y, it's going to be XY, they are the same, or X bar Y bar, and they are the same. This is for the XOR and XNOR. These are identities for the XOR. If you are doing X XOR 0, it remains a 0. If you do x XOR 1, it will become the complement of it, which is x bar. X XOR x is equal to 0. And notice, if you put 0, 0, it will give you a 0. And 1, 1, it will give you a 1, because XOR, they must be different to give you a 1. Here in x XOR x bar, they are different, okay? So it will give you a 1. You need to know that x XOR y is the same as y XOR z, but here you should be careful that when you have two XOR, you cannot use one XOR for three variables, x, y, z, like we do in the OR. You must use two XOR. So you do x XOR y, the output, you do XOR for it with a z. I'll show you the figure. This is the symbol of XOR. This is the symbol of x NOR, okay? When you are drawing 3x XOR y XOR z, look please how do you draw it. You either do x XOR y, the output, you do XOR for it with a z to get an f. Clear? We do not do x XOR y XOR z in one x. It only takes two input. Okay, you need to know that the XOR only take two input. It does not take three. So if I am doing x NOR, check this please. I do y XOR z in the first one, and I do y XOR z, and their answers I do x NOR for them, because here I have XOR with a bar. It becomes an x NOR. So this is the first XOR, this is the second XOR, and this is an x NOR. Okay? Now, we have one last gate in this chapter, which is the high impedance gate. Let me show you what it is. It is easier with the graph. You have here an input. It could be a 0 or it could be a 1. You have here an enable. If the enable is a 0, this as if it doesn't matter what is the input, I am not getting any output. If the enable is 1, now I check the input. If input is 0, I get a 0. If input is 1, I get a 1. This looks exactly like a buffer, but you put a switch to it or an enable. Let me read the truth table with you. You have a 0. We don't care what is the input. I will get high Z. High Z means no output. If the enable is 1, now I worry about the input. If enable is 1, input 0, a 0 will pass. If enable is 1 and input is 1, 1 will pass. So I repeat, enable, it is like a switch. If a switch is off, nothing you will not get any output. If the enable is 1, now you check what is the input. Okay, so this is end of chapter 2.